Thanks for being here. And as we heard in the plenary talks, a lot has happened since the first ASIC in 2018. A big factor really is just how many sensors have been deployed and how much data has been generated with all the governmental, industry, and philanthropic investments that have come over the years. And the low-cost sensor technologies have democratized air monitoring and provided information in places that were under-monitored and overburdened with air pollution. And when we speak, when I say we, I work at the California Air Resources Board. So when we speak with community residents and with community-based organizations, they ultimately want action that protects their health, their family's health, their community's health. And I think we're at the stage now where we can kind of take a look back on innovative air monitoring projects that have gone on around the world and look for blueprints of how air sensor monitoring can lead to action. And so in this section on challenges and successes in community air monitoring, we'll hear about lessons learned over years of community monitoring, how new technologies have been used to tackle monitoring objectives, what approaches have been effective and what hasn't been effective, and how the data is being leveraged to create that action to make a meaningful difference in people's lives and health. We're going to have Caroline Frischmon speak first. She's a researcher at UC Boulder, and her talk is Community-Based Exploration of Environmental and Human Health Impacts of Industrial Air Pollution in Pascagoula. Pascagoula.
Thank you. All right, hi everybody. I'm Caroline Frischmon. I'm a student in the Hannigan Air Quality Lab at the University of Colorado Boulder. And this is my work in Pascagoula, Mississippi. So I'm specifically focused in the Cherokee Forest neighborhood of Pascagoula. So this is a neighborhood right on the coast of the Gulf of Mexico, and is also fence lined to a large industrial park, which includes a Chevron refinery and a large shipbuilding yard. So to give you an idea of the proximity of this neighborhood to the industry, this is a photo I took standing on the street of the neighborhood and looking through the trees. You can see the large ship that's being repaired, and then behind that are flares from the refinery. So I got connected with this community through the American Geophysical Union's Thriving Earth Exchange, which is a program that pairs communities and scientists together to work on a local issue. I specifically worked with the Cherokee Concerned Citizens, which is the local organization in the neighborhood, with Barbara, Jennifer, and Leah, and also with Dr. Kathy Duderstadt at the University of New Hampshire. So the Cherokee Concerned Citizens has spent the last decade or so reporting widespread odor and health impacts in the neighborhood. So this is a survey that they did in 2021 of many reports of odors and different health symptoms. And while they've been able to document all of this, their challenge has been to link it directly to the industrial pollution. And that's really been an obstacle for them, because it's allowed conversations with local officials to stall at, it isn't the pollution or it isn't the industries that are making you sick. And so in our project, their goal was really to uncover the link between the health impacts and the industrial pollution, so they can move forward in their organizing. And woven into that was our academic goal to explore how semi-quantitative or uncalibrated low-cost sensor data can be used by communities to better understand air pollution sources and patterns, not necessarily concentration. So this is a very small scale pilot project, so we didn't have the resources to conduct extensive calibrations and co-locations, but I really believe there's still a lot of underexplored potential for low-cost sensors in these settings to still provide really impactful data, specifically about patterns in this context. So the way we did this is we deployed low-cost sensors in the community, and that's still ongoing. This is a photo of one of them. During part of that time, we had resident participants record any odors or symptoms that they noticed, so we can see in time whether there's overlap. So this is an example of one where somebody reported a strong chemical smell and itchy burning eyes and a sore throat in February. We placed 2 of our monitors, which we call pods, in the neighborhood, which is outlined in red. And then we also had one across town And this was really important for the community because they really want to show that this is a problem specific to their neighborhood, and what the air that they're breathing is different than the air the rest of Pascagoula is breathing. This is a look inside of our pods. We have many different sensors. I'm only going to talk about 3 of them today, which are sensitive to VOCs, amine series, and sulfurous odors and ammonia. We also have, I'm not going to talk about the alpha sense or the Figaro 2602 because we found these are really sensitive to humidity, and Mississippi is a very humid place to be doing this research in. So we're still making sense of that data. And then I just don't have time to talk about PM2.5, but I'm happy to answer any questions about it. This is a look at the raw sensor data, just at a glance. It looks like the PowerPoint has kind of shifted the text around a little bit, but you can see how the baseline of this VOC sensor is really tracking with humidity, which is the orange dots. But we also see some distinct spikes that are unrelated to the humidity trends. And so we really want to focus on these spikes, but you can imagine showing this plot to a community group would be sort of misleading or confusing because you might be led to think that February 29th, for example, has really low VOC levels when we know that that's more to do with humidity. So what we wanted to do was find a way to separate the spikes from the humidity impacts. And we did that using a pollution episode detection algorithm. So it was derivative based. So basically when the sensor reading increased rapidly, which would mean the derivative goes above a threshold, we took that as an episode was detected, and then the episode ends when the sensor reading returns to the value at the start of the episode. And then we removed all non-episode data from our analysis. So we're no longer looking at long-term, because we don't have concentrations, we really can't look at long-term trends. We're just focusing in on what's happening with these episodes. And when we do that, this is what the data looks like. So the top 2 time series are in the neighborhood, and then the bottom one is outside of the neighborhood. I again apologize for all the text that has moved around. But you can see first that there's many more episodes within the neighborhood in the top 2 time series, and those episodes tend to be more intense other than on the 26th. These episodes they average about 35 minutes, but they have ranged from 2 minutes to 2 hours. And you can see that the way that we're referencing these sensors, because they're not calibrated to a specific pollutant, we can't say this is ammonia or this is VOC. So we're saying that they're VOC related, rotten odor related, and ammonia related when we're talking to community members. And actually one other thing I wanted to say, I don't know if you can see it on the screen, but many of them are all 3 of them are spiking together, which is helpful to see that it's not just an anomaly of one of the sensors, that they're all sort of seeing an episode at the same time. Another thing that helps us see that we're looking at the right thing and we're looking at the pollution from the industry is looking at wind direction. These episodes are happening when the wind is coming from the direction of the industrial park, and they're most intense in that direction as well. And then lastly, when we look at the symptom and odor logs, many of the days do line up. Like, for example, on March 1st, people reported itchy, red, watery, burning eyes, and we saw episodes throughout that day. But there are some days, like on February 12th, where people reported odors throughout the neighborhood, but we really didn't see a significant episode that day. So we're still looking to why that might be, but 2 possible reasons are we're not measuring every pollutant. So people could be reporting something that we just aren't measuring. And then we see some variation in when episodes are happening between the 2 pods within the neighborhood. So these aren't big plumes that are covering the entire area. So somebody might be noticing something that's not where the pod is at. So that's an overview of the data. Now, the really important thing is, what is the community going to do with this data? So last week we were in Mississippi and we shared the data about that have already been emerging throughout the process of this work. So the first is the way that validation leads to activation. So the word validation came up a lot in our conversations. This has been people have been recording this problem for over 10 years, but this was the first time that it was laid out in front of them in a visible way. And so people talked a lot about how validating that felt and that they didn't feel so crazy anymore. And what was exciting for us is seeing the way that validation leads to activation, because when you're told you're not crazy and you lose that second guessing. People really wanted to take action then. So this is a photo of someone who wrote the phone number of the Mississippi Department of Environmental Quality complaint line because they were excited to start recording these incidences on a legal level to move forward with. So this outcome is really exciting for the community organizers on our research team who have been trying to get more and more people involved in their organization. The second one is the way this data is helpful for communities, their efforts to document industrial activities. So when we set the pods up, we were experiencing a lot of smells ourselves. And then in the days following, we saw a lot of episodes and many people reported symptoms and odors, which are shown in the table with some quotes from people. And so when we dug deeper into these days, we found that Chevron refinery reported a permit deviation and flaring just a day before while we were setting up the monitors and noticing the smells. And so we can't say exactly what was happening at the refinery in the days after, but this is an example of how it's helpful for the community to have this information to track what is happening in their neighborhood during times of increased industrial activity or in the days, around the time of a permit violation. And then the last outcome is the way that we're using this data to inform the Mississippi Department of Environmental Quality. So they will be collecting 24-hour VOC samples starting in July through an enhanced air quality monitoring program from the American Rescue Plan. And so 24-hour samples are going to be helpful for understanding the longer term exposure, which we weren't able to look at. But from the data that we collected, we also showed that that's going to miss part of the story in this neighborhood, because a 24-hour sample is not going to accurately characterize these short episodes that we're seeing. And so we're using this data to push them to also take 1-hour SPOD triggered canister samples so that they can tell us what exactly is in these episodes that we're tracking. So that isn't confirmed yet, but we're hopeful that it will happen. So in conclusion, we use semi-quantitative low-cost sensor data to validate residents' experiences of adverse impacts in a fence line community. This semi-quantitative data focused on patterns of pollution episodes near and far from a source, but did not provide concentrations. And now we're analyzing the use and impact of this data in the community, and we're excited to see the ways that it's already helping to inform their work. So thank you all for listening. Thank you to my awesome group of researchers that I get to work with and our funding from CU Boulder, the American Geophysical Union, and the University of New Hampshire.
So I'm from Galena Park, Texas. My name is Cruz and Hosa with the Environmental Community Advocates of Galena Park. We're going through the same thing. We've got maybe 3 years worth of data. We would our data by hosting farmers markets and giving vouchers to people to fill out a health survey. So you're saying you need probably 10 years worth of data?
No, so that they have been working on this for 10 years. And they've been doing, like, their organization started 10 years ago. But what I just presented was only a couple months of data and 1 month of the symptom and odor logging. But they have surveys from the past that I also referenced just to kind of show how long they've been at this.
Hi, I'm wondering if you could talk a little bit more about the community surveys. Like, how often would people fill those out? Would it just be when they're experiencing something, or would you get data like other times as well? How many responses do you get? Could you comment on some of that too?
Yeah, so we had them fill it out whenever people noticed the odor or symptom. And then we had them note what they were doing, and a lot of times it was when they were taking out the trash or grabbing the mail anytime they went outside. So we probably are missing a lot because people, like, if they're just not outside, they're not noticing it. But I would say there were probably half of the days there was at least one report of something. And then, like I showed at the very start, there were days where 4 out of 7 people were reporting a similar odor or symptom.
And so roughly how many people were filling out surveys? Like, how many people had the opportunity?
I think at most we had, I think it was around 10, and it kind of dropped off a little bit towards the end, but that's what we started with.
All right, thank you.
Yeah, thanks. It is a small community. It's only about 100 households. So we're starting with a small pool already.
Can I just ask a follow-up on that? I was curious whether you had chosen on purpose not to use something like Survey 123, like a phone app survey, because
Yeah.
technology.
So we had the paper survey that I showed, and we had a Google form. The paper surveys were much more popular because this is, it's an older population. It's a lot of retired folks. And so they liked just writing out. And that's actually, before I've worked with them, they have done a similar symptom and odor logging without the simultaneous air monitoring. And they had done the paper survey. So people were just a little more familiar. Yeah.
Thanks.
All right, thank our speaker again. We're going to wrap up there. Our next speaker is going to be our first scheduled John Downie with Environmental Instruments Limited.
Hi everyone, I'm John from Environmental Instruments, and I'm going to talk about several key lessons we've learned over the past decade of being involved in community air quality monitoring projects around the world. Some lessons may be familiar to those who are currently running monitoring projects, which we hope is reassuring that you're not alone in the challenges that you have faced. I can certainly see a theme from the kind of introductory talks as well. For those who haven't heard of us, we are a manufacturer of AQMesh small sensor systems based in Stratford-upon-Avon in the UK. We've been involved in a huge range of projects over the past 10 years, with many revolving around community monitoring, including globally recognized programs such as the groundbreaking CitySense project over a decade ago, to current exciting projects in Dallas, San Diego, and Minnesota. AQMesh pods are currently in use across 6 continents in 75 countries, with over 500 individual organizations, government departments, and companies from a wide range of industries. Whether it's monitoring communities affected by a local industrial plant, or raising awareness about pollution caused by school drop-off, no 2 projects we've been involved with have been the same, but many lessons learned can be grouped into a number of small key categories. Today, I'll be running through the main learnings from a manufacturer's perspective of scoping a project, choosing monitoring locations, data communications and accessibility, calibration, instrument choice, deployment, and finally keeping your project going. A question we are asked when we're approached with any potential project is, what are the key objectives? Objectives need to consider available resources such as budget, size of your team and their other responsibilities, and the expected timeline for results from stakeholders. We've seen a lot achieved with a small dedicated team, for example, local housing associations with a small area to consider, whereas larger community projects can often take longer due to environmental protection responsibilities, which are more visible or widely known for communities, such as noise or water. Studies have shown some pollution, such as NO2 and PM2.5, can be far more regional than previously thought, with sources being long distances away across county, state, or even country borders. Making a community aware of how to reduce their exposure to this type of pollution, therefore, might have greater benefits to the community than encouraging mitigation. Larger impact with local mitigation measures can often be made with more transient pollutants such as H2S, SO2, ethylene oxide, TVOC, and larger particle fractions which remain suspended for short periods of time. We also find that projects can change very quickly due to local, national, or global politics and policy changes. Successful projects can cope with these changes, often by engaging the community as early as possible. While politics can change, the expectation of the community is often less quick to deviate. Once you've scoped your project, locations and positioning of monitors will need to be considered. One of the biggest causes of delays to the start of a project we have seen is not only consideration of where to place monitors, taking into account equal representation of the community, but also who owns the infrastructure at the intended locations and what permissions are required to install. This is certainly the case with larger projects covering wide areas, such as the Breathe London pilot and our initial project with the Minnesota Pollution Control Agency. Power is a big consideration, and most manufacturers will have a range of solutions, including external mains, batteries, solar power, or a combination of all. We have seen pods mounted on lampposts, tapping into mains power supply, which is only powered during the nighttime, non-weatherproof PSUs filled with water, and solar panels facing large buildings, causing shadows and blocking any direct sunlight. With varying technologies used between manufacturers for sensing and battery backup, along with differences in power consumption, some may be able to better cope with these situations than others, but you'll want to be aware of this before dedicating resource to installing in that location. The same can be said for high voltage equipment causing EMF interference, with sensitive sensors which can be introduced by dirty power supplies as well, without the proper protection. Security of hardware is one of the main reasons why many monitors are placed at more than 3 meters of height, but we have not found this to be much of an issue in many locations. Discussions at ASIC Ghana showed how engaging with the community early can bring about a sense of ownership of the equipment and the outcomes, which offers the best possible protection for the project and its assets. Moving on to the information you want out of your sensor system, the data. In our experience, where there are communities, there are cell phones. Therefore, this is usually the most reliable means of getting data from an instrument to a place which is accessible, such as a web application. Very remote locations can involve local SIM cards, which can usually be used by amending a few simple settings. Manufacturers now also offer APIs where data can be called from an initial processing and storage cloud server onto a customer's own database. In many cases, these are public-facing websites or applications, but there are considerations to be made here also. Programming resources are often required, and workloads can cause delays in having the data published, frustrating the communities wanting to see the data. Manufacturers can also offer their own quality assurance protocols, or in our case, flags against each data point, providing information on the reading being okay, or any potential reasons the data point might be erroneous. How or if this information is provided to the public needs to be considered to avoid confusion or the potential for misinterpretation and loss of confidence in the data by the community. Quality assurance of small sensor systems is now a large focus for many projects, and there are more standards, documents, and guides than ever to help. Field calibration of small sensors cannot be achieved using the same approach as used for FRM. Therefore, factory calibration in ambient air is often being used to increase out-of-the-box accuracy and demonstrate agreement with reference or equivalence instruments at the manufacturer's site. This is also a great way for manufacturers to demonstrate repeatability and precision of their instruments, which is important to ensure monitors in separate locations are comparable. Environmental conditions at the manufacturer and where a community needs to monitor are rarely the same. So how can you be confident your chosen instrument works in all climates? Techniques to locally calibrate small sensor systems have been developed to demonstrate an increase in instrument accuracy in local conditions. And the most appropriate will depend on your available resource and the number of nodes you have. Transferring a known reference to a small sensor system involves a co-location with FRM or FEM instrument for a period of approximately 1 to 2 weeks. In some cases, this is used as a training period for AI or machine learning, and in others used to apply calibration factors such as slope and offset value. We've noticed it becoming increasingly more difficult for government reference locations to be used for this type of calibration in the past decade, and therefore asking your sensor manufacturer for advice is recommended. New techniques such as long-distance scaling drastically reduce the resources required for large networks and can incorporate data from reference instruments to further increase confidence in network data. This was carried out by the University of Cambridge with AQMesh data during the Breed London pilot and has since been applied to smaller scale for projects in the UK and Canada. So which instrument should you choose? Some instruments are obviously more expensive than others, so you'll need to weigh up the choice of having more nodes versus high quality data, more proven hardware and algorithms, or more offered in terms of support or high-tech data analytics. It's also worth looking past the initial purchase price to determine the cost over the course of your project, including support packages and consumable replacements. Hybrid networks of small sensors can provide advantages, and rentals may also be a better option for short-term projects. We're looking forward to certification becoming increasingly available for indicative systems in the future, with groups in the UK and Europe working on this for a while already. In the US, European standards may be required less, but will provide a good indication of quality of data, which can be collected from an instrument before ASTM specifications are also released. In our own experience, data ownership has been a very important consideration, especially for government agencies. And while many manufacturers are clear that all the data belongs to the user, this is not always the case and worth double checking. Knowing what is involved before installation is paramount for preventing delays. Manufacturers will have done their best to ensure their solution is as easy as possible to install, and will provide installation guidance such as manuals, quick start guides, and videos. But we have found communication between management and ground teams doesn't always mean they reach the right people in time for deployment. Health and safety will always need to be considered in terms of manual handling and working at height, and mobile work platforms sometimes need to be hired. Potentially, our biggest learning in this area is ensuring the installer does not leave the site without confirming the instrument is connecting to a required mobile network or cloud server. Your manufacturer should be able to tell you what data should be expected to be transmitted and when. Therefore, a few extra minutes on site here could save potentially costly revisits. Your project is now up and running, so keeping it running should be the easy part. And if the previous 6 learning points have been covered, this should be the case. If you have clarified the ongoing requirements of a particular system, and they are normally minimal, there should be very few surprises for your project going on. Hardware has come a long way in the last 10 years, allowing over-the-air firmware upgrades, increased storage capabilities in the case of network outages, and remote power cycles. It's amazing how much can be fixed with a simple off and on again. Accidents and unforeseen issues always happen. For example, HGVs backing into them, or the pole they are mounted on coming unstuck in a cyclone. But these should be in the minority, so having a robust modular instrument which can be repaired is beneficial. That's where support from the manufacturer representative comes in. People also move on from jobs, so keeping a up-to-date project log is always recommended. Wrapping up, our most important lessons have been that a successful project is well planned, considering all stakeholders from the beginning. Resources need to be considered early, and there are benefits to engaging with the community early too. The project needs to have flexibility to be able to cope with unforeseen challenges or the data simply not proving what you'd hoped it would. And finally, choose the instrument or instruments which best fits your overall project, considering your environment and monitoring aspirations. Finally, thanks to UC Davis for hosting this fantastic event and giving us the opportunity to share our experiences. And thanks to you all for attending. We can't go into much detail in a short presentation. Therefore, if you'd like to find out more, please grab me during a break or head over to see Ambi Labs, our North American partner, booth 407.
I'll begin. I believe you posted a poll as part of your presentation, right? And I noticed that I responded to it. And I noticed that you've got some answers that came in. And the poll question was on co-location, or sorry, it was on calibration, with co-location being one of a few different types of co-location. I was curious if you could comment on that. I don't know if you've seen the latest results, but co-location was by far the most popular, with seasonal co-location being the single most. Can you comment on some of those calibration methods and maybe recommendations or thoughts, in particular on some of the less popular calibration methods, such as desk-based calibration?
Yeah, so I think the desk-based calibration comes on with very large networks where obviously installing equipment either in one place at the start or having a single pod that goes around each location can become very costly with resource. Kind of finding a place where you can install 25, 50 monitors at one place can be quite difficult, especially with power supplies, solar panels and all that kind of stuff. So kind of the new network or the new developments with long distance scaling, as we call it, where effectively you're pulling out the hyper local events. So any peaks in different pollutants, you kind of pull those out and you end up with a baseline that you can calibrate all the sensors to. And obviously if you have reference data within that particular area, you can include that and therefore scale the baselines to the reference data as well, so that you can kind of compare everything together. So that's worked very well when you have very, very large distances to cover. The Breed London pilot had 100 AQMesh pods with 30 reference stations, and all of the data was pulled in. The analysis was done by the University of Cambridge, so that became very helpful. When you've only got a couple of monitors, it becomes a lot easier to co-locate them together. But as I said in the talk, we found it quite hard for people to be able to access reference stations. So I know there's companies that are offering kind of mobile and kind of trailer-based FEM instruments where you can then co-locate the pod next to that. So and it is still the best way to do it. I mean, we've had people who have tried to effectively calibrate using bottled gases, but because the sensors are sensitive to humidity and temperature, squirting a dry bottled gas, you get a response from that temperature and humidity change rather than the actual gas that you're looking to kind of draw out. So we've had people try it. Some have been more successful than others, but so there are a wide range, and obviously we don't use AI, but I know a number of other companies are.
Thank you again for your talk.
No.
So our next speaker is going to be speaking remotely, and it will be Amirhossein Hassani, who's a scientist at NILU Climate and Environmental Research Institute in Norway. And he's going to speak on household heating and induced PM2.5 Levels Association with Meteorology and insights from a community-operated low-cost sensor network.
Yeah, this presentation will be a successful example of what John was presenting now. For example, this is a project, a community-based project in Poland between 2020 and 2022. And we have used local sensors there to monitor PM2.5 in particular. So I will give more context about the project and what were the results, how we successfully use the sensors. I mean, it's this presentation is kind of an example of the general details of a project. I mean, what John presented in the previous presentation. As I mentioned, yeah, this is a project about converting the solid fuel furnace, or in general the heat solid fuel heat burners in Legionowo in Poland. It's a city close to Warsaw in Poland, and the project was to monitor the PM2.5 as a result of solid fuel burning in Legionowo. And the main idea was to monitor the hottest spots of the PM2.5 emission. So this has two advantages. First, for the community to increase the awareness for knowledge increase, and the second was for the authorities and the regulatory purposes to have a better overview of the hottest spots of emissions, and probably investing more on converting the traditional fossil or solid fuel burners, because typically in Poland they use coal for household heating, and especially in the winter it can cause a lot of problems for the health in the neighborhoods. So the overall question in this project was how we can explore the spatiotemporal dynamics of particulate matter, or PM2.5, generated by a household heat using the local sensors operated by citizens. So it is an example of the community operated or citizen operated sensors. So we use the early sensors in this case. So we hand out around 10 to 15 sensors, and we had multiple workshops with the community, with the people in the neighborhoods in the Legionowo for installing the sensors. And as a result, we had a network of 15 sensors from 2020 to 2023. And as I mentioned, the main objective was to convert this local sensor data from the community to something more trustable, something with higher quality for regulatory purposes, and at the same time, the rising awareness. So in this project, we didn't do this co-location, this classic thing for evaluating the accuracy of the sensors because of the cost, and also because of the time of the project. I mean, the duration of the project. So we prefer just to install the sensors, and we do this remote calibration or remote quality control assurance techniques in our project. So to achieve this goal, we suggested a few data quality assurance techniques or processing framework, and also we try to quantify the relative humidity of the sensor remotely without co-location. And finally, we thought how we can make this data digestible for for example, the authorities, how this data can be useful. And I will explain later. I mean, for example, we use the machine learning for evaluating the relation between the PM2.5 levels and the meteorology in Legionowo. So this figure is not relevant to Legionowo. This is a co-location or sensor-to-sensor comparison we had before in 2023, just to evaluate how the early sensors, earlier made also in Poland from the company in Krakow. So we try to evaluate the sensor-to-sensor variability. And in general, for example, here from 16 sensors, overall the quality was very good, and except one sensor, but even that sensor also had like a correlation of 0.8 with other sensors. So this was just as one of the basic steps for quality control of the sensor. So this is the overview of the data gathered during this period from January 20 to January 23. So you see the spatiotemporal or the temporal coverage of the data wasn't the same because this was an I mean, the citizens were running these sensors, and it was very difficult to find sensors to operate the sensors for. So as a result, we have this was one of the challenges. I mean, using this community-based sensor or community-based operated sensors for monitoring PM2.5 in the project. So as I mentioned, we proposed a three-stage pre-processing to improve the quality of the data. Just the first step was to finding the sensors with enough data coverage during each month, and then for each sensor we found a correlation between the sensor and the nearby network, and if it was above a certain value, in this case 0.75, we assume the data of that sensor during that month is reliable. And finally, we try to address this sensor drift, how sensors are performing against the reference station. So in Legionovo, we had only one reference station in the city center. So we evaluated the bias of the sensors from the reference, and in the case of increasing or decreasing bias, we were able to detect the sensor drift in that case, which in this case we didn't have such problems. So overall, the quality of these early PM sensors were very high. So this is, for example, Warsaw is very close to Legionovo, and these are the air quality reference air quality stations, the diurnal variation in PM2.5. So we use these stations to find which periods we have lower spatial variability in the city, and then to compare the sensors with each other to find the highest correlation between the sensors. Let's keep this sensor. Another thing, as I mentioned, we didn't have any official collocation. So to make data more reliable for regulatory purposes, or for to make data decision ready, we had also this kind of remote evaluation of the relative humidity uncertainty. So we divided the sensors measurements into different bins, and for example, from 50 to 100% relative humidity episodes. So in each bin, we calculated the bias of the sensors from the reference station during the periods of the day that we had the lowest variability in the PM2.5, especially during the summer. And we fitted normal distribution function to calculate the uncertainty of the sensors. So these are the results after applying this quality control assurance to the data. So it provides an overview of the quality of the PM2.5 during different seasons in Legionovo. And as you see, it is hugely correlated with the air temperature, because as I mentioned, the main source of this PM2.5, which is almost more than 65% in Poland, the source is solid fuel burning, especially the coal burning during the winter. So when we have the lower temperature periods, we have higher PM2.5 measured across the city. And this is a better view of the spatial variability of the PM2.5 measured by the sensors using after this data quality assurance. And this data, for example, matched our, for example, we had some interviews with the citizens, and for example, in these regions in the north of the city with higher reported PM2.5, we have more complaints from the citizens that, for example, we have the waste burning in that region. Some citizens were complaining from their neighborhoods. Why they burn, for example, garbage or waste in that region? So overall, this data was matched with the observations from the citizens. Another usage of this data was to predict the PM2.5. We used the GAMS models, general additive models, to predict the PM2.5. So if I want to make it short, the main application of this is if you have the sensor data and one reference station in the city, then it can make us able to predict or forecast the PM2.5 based on the temperature and relative humidity data. So another application of this statistical model development was to see what is the relation between the meteorology in the region with the PM2.5 levels. And for example, here we have different parameters like wind speed or temperature, and also the relative humidity. So the increase in each of these parameters, it shows how the PM2.5 deviates from the average using this accumulated local effects plot. So overall, if I want to summarize this project was a successful example of the using local sensors for making decision-ready results, making insights, both scientific and also suitable for the regulatory purposes. For example, to detect the hottest spots of this PM2.5 level is better. I don't say PM2.5 emission.
I mean, I have a question. I was curious whether the burning, did you mention that there was some outdoor burning going on, or whether this, you think this is more indoor home heating, and based on finding here, and that being one of the main sources of the PM, if there are any kind of follow-up actions from this data that the city might be using?
Yeah, exactly. So as I mentioned, the main source is the solid fuel burning and from the furnaces. So using this data, we shared with the local community, and also we shared with the municipality in Legunovo. They are trying to offer the citizens in that region for something more sustainable. For example, they shift into the electric heaters, for example, in their places. And also we have another project, continuation of this project is to install the sensors indoor and then compare, for example, the ratios between PM2.5 indoor and outdoor, especially to have a better understanding of how this solid fuel is affecting the indoor environment as well. But if I want to answer you, yes, this data is now for the municipality to offer the citizens for installing the heaters.
Our next speaker is going to be one of our invited speakers for the session. Scott Hersey is an associate professor at Olin College, as well as founder and lead at Air Partners. And Scott's going to be speaking about impact-driven stakeholder-partnered air justice research in Boston, Massachusetts.
Right. I'm Scott Hersey. I'm joined at this conference by my colleague Francesca Mahouf, who's the research program manager for Air Partners. And I'm going to tell you a little bit. The focus of this talk is going to be more the model of partnership in these types of community-based projects and less about sensor validation. The Air Partners Group, our mission is to support environmental justice communities in their work that they're already doing to breathe cleaner air. We work by 3 guiding principles. The first is that we are continually seeking to decenter our own academic priorities so that we can center community priorities. Second is that we're always working to meaningfully share decision-making power in the projects that we do with community partners. And the last is that we have a bias toward impact in all of our work. And impact, importantly here, is defined by our community partners. Our community partners have never heard of the term impact factor, nor do they care about it, and so neither do we. We have been working in the Boston area for 8 years. We've had over a dozen partnerships in the area with different municipalities and nonprofit organizations. I'm going to focus today on a project that we've been doing for the last 3 years with a partner called Alternatives for Community and the Environment, or ACE. It's in the community of Roxbury in Boston. And over the course of these 8 years and all these projects that we've done, we started out by basically doing proof of concept little projects with different partners. And in our last grant that we got, one of the meta level goals was to articulate a model that we use for doing these types of projects moving forward. And this is the model. We call this our roadmap, and it's every phase. There are 7 phases to a project that we do. Every phase has a descriptive title. There are goals related to each one of those phases. There are activities for air partners or another academic partner, as well as for a community partner. And then there's a set of associated products so that you know if you've been successful in that phase. I'm going to draw your attention to just a couple things quickly. First is that there's this set of activities with clearly defined roles for air partners and for community partners, and much of that work is collaborative. The second thing to draw your attention to is that we're very intentional at the outset about this phase 1 of identifying stakeholder priorities. A couple of speakers have alluded to this. Getting on the same page about priorities is really, really important. I've never spent too much time doing that. And have only had issues on the back end by not doing enough of that. So I want to make this a little bit more real by walking through a case study for our project in Roxbury. Roxbury is a predominantly Black community in Boston. It is a redlined community that has experienced an enormous amount of environmental racism. And we got connected with Alternatives for Community and Environment, who is a decades-old environmental justice advocacy group that centers on addressing systemic injustices around Roxbury. Our primary partner is Emmanuel DeBarros. He's the Director of Community Engagement and Development. So I told you we spent a lot of time in that first phase, and in that first phase, we are identifying stakeholder priorities. What this looks like in practice is showing up in the community and having a lot of open-ended conversations and some scaffolded conversations. And primarily what we're doing there is we're trying to understand what are the priorities of our partner and how do those intersect with things that we can bring data to. Along the way, we're also building a lot of trust. When you show up continually in a community and you're listening, there's a lot of trust that gets built. So in the first phase of this project, we left with questions. These were key questions that we wanted to answer with the project that we were doing collaboratively. Things like, what's the air quality impact of Nubian bus station, the Fairmount commuter rail line? To what extent are air purifiers able to reduce exposure to particulate matter indoors? So these became our guiding questions for the project that we planned together. Once we had these guiding questions, there was a lot of Francesca and I going back and developing a study plan for how to address those questions, taking it to our partners at ACE, getting feedback from them, getting input and iterating. So that was really just taking these stakeholder priorities and translating it into a project plan. In phase 3 is when we started collecting data. And in starting collecting data, again, we're taking cues from what our community partners' goals are. The goal here is not just to collect data. The goal here is to support our partners. And our partners wanted to build capacity with their youth environmental education program, or the REAPers. And so when we're installing sensors, we designed training materials and we ran workshops with REAPers, and they installed sensors and we installed sensors with them. Once we collected data for 2 to 3 years, depending on the sensor, we spent a lot of quality time in R, and we generated some key figures that helped us generate some insights from our air quality network of 19 sensors. And this was a lot of us doing technical work. This was a lot of data analysis that our partners didn't have the capacity or interest in doing. So what this looked like is us generating key figures, and then in weekly meetings, presenting those to our partners and saying, hey, we're finding this at this site. What do you think? And along the way, they would say things like, oh, would your sensors see construction emissions? And we say, yes. They say, oh, because there's 2 major construction projects happening right around that sensor. I wonder if that's what's going on. So they're meaningfully contributing to data interpretation. And that brings us up to relatively current. We are wrapping up phase 5 of this project right now as we end our grant and project with ACE. And we've been doing a lot of work creating artifacts, and I want to walk you through a little bit of what that process looks like. So I teach at a undergrad institution, there's 350 total students. They're all engineering, they're all undergrads. And one of the missions of Olin is to do real world project-based work in the classroom. And so this came into the classroom. And the first step in creating artifacts is to send our students out to join ACE events like canvassing, community meetings, and like legislative lobbying events, and see how ACE actually does their advocacy work so that they can figure out what they need to make to support ACE's work. I taught a class this last semester on environmental analysis where I coach students through the process of the air quality data science. They learned those fundamentals and they generated a first draft of insights from this network of 19 sensors. And Manny from ACE came to class. He got to engage with those insights and give feedback. And then we handed all that off to a capstone team who created some wireframe sketches for what those final deliverables might look like. They got feedback on those wireframes from ACE and then created some final one-pagers and posters. Here's an example of what some of these one-pagers and posters look like. Keep in mind that this is from a network of 19 sensors in an extremely complex urban environment, but the stories you see in these one-pagers and posters are pretty straightforward. And that's because these straightforward questions are what ACE needs to effectively do their advocacy work. They can't present a really complex, nuanced air quality story to an elected official and expect it to do anything. So we have posters focused on, I live near a construction site. Does it affect my air? A couple of key figures. And then importantly, also most of our posters have some kind of action item of what can you do next? We also, in addition to handing these off to ACE for ACE to use in their advocacy work, we have participated in setting up and running data walks where we take posters. We host community events that have typically really good Dominican food. And we have kind of a party where people walk around and they engage with data. We talk to them about the insights from the data. And again, there's a bias toward action of getting people involved with ACE work, with other environmental advocacy groups and work that they're doing. We also created a long form web story for ACE and one of our other partners, the Fairmount Indigo CDC Collaborative. There is a bill in the Massachusetts legislature right now focused on electrifying commuter rail lines that are currently powered by diesel. And so they wanted tools to tell the story of why that matters. So we created a long form web story to do some of that work that focuses partially on the air quality impacts of the diesel commuter rail, but also a lot on people's experience with the commuter rail, because that's what our partners wanted to get information out about. And so that puts us firmly in the space of leveraging artifacts. And I'm going to share a little bit about what that looks like right now. I mentioned that a lot of what our students have made is one-pagers. And if you look on the far left, that's because a lot of what ACE does is canvassing. They walk around in their community with clipboards and they tell people stories. And so if they can put a one-pager on a clipboard and tell a story to people that they're talking with, then their work is more effective. They also take these one-pagers and also posters to community meetings. And also they show up at the State House on a regular basis. And in fact, tomorrow morning, they're taking a bunch of youth to the State House for an environmental health lobbying session and taking one-pagers and posters related to HEPA air purifier pilots that we've been doing. I'm just going to close with a couple of short lessons learned. There's a whole bunch more, but I'm going to share two. And the first is that we have learned the hard way that a lot of challenges in these projects result from misaligned goals and expectations between community and academic partners. Francesca is speaking on a panel on lessons learned the hard way this afternoon, I think at 3:55, is that right? Yeah. So you can hear more from her about that, but I'm just going to share really briefly, kind of meta level, what does that mean? I said that we spend a lot of time in phase one, and a lot of what we're doing in phase one is imagining what's going to happen in phases 5 and 6 and getting really clear with our partners about what they need to have in their hands to be successful there. So we're beginning with the end in mind, and that's, you know, basically carbon copy of what Tim Dye said this morning in the plenary. And I promise these slides existed before you. And that's because a lot of the problems show up in phases 5 and 6. Because community partners weren't meaningfully involved in previous parts of the project, or because that first phase never happened or never sufficiently happened to get on the same page. And the second lesson that I'll share briefly and then I'll close is that simple stories hold the greatest potential for impact. And this is related to what I was talking about on those one-pager slides. We've got a network of 19 sensors in a highly complex urban environment. I can't underscore how tricky it is to tell stories from those data. But a lot of our work as data scientists is to sift through what are the actual stories that are there in the data, and then to tell simple stories. And it's not because our partners can't handle complex stories, but it's because when they show up with people who are making decisions, simple stories are the currency that actually achieve impact. Again, yeah, we're taking these complex data, turning them into really clear one-pagers. Do air purifiers work? Yeah, they do. Here's a couple figures that tell you that they work, and here's what you can do to get one in your house. A couple next steps, there's legislative advocacy happening at the Massachusetts State House. A lot of that is happening in commuter rail electrification as well as MBTA bus electrification. The artifacts that we're creating are going into supporting our advocacy partners in doing that. And we're in the process of sunsetting this project with ACE and developing new partnerships and finding funding to do this model in other places. So that's where we are.
Hi, Taylor Schulte. Thank you so much for your presentation. It was wonderful. I was curious whether you financially compensate individuals who participate in the work. What is that arrangement like? And if you have a bit of time, could you hint at what you're thinking around sunsetting? Because I think a lot about that with the projects that I do as well.
Yeah, great question. So we do financially compensate folks. Our partners at ACE we got this grant together and it funded a full-time position for them for the duration of the project. For people who are participating in the project, the folks who are involved with the HEPA air purifier pilot, when we install an air purifier for a pilot program, they get to keep it. That's not direct financial compensation, but I've worked on some other projects where we're trying to understand the health impact of an air purifier. We're going to tell you that it improves your health, and then we're going to take it away at the end. So we should take a different approach, and we have a bunch of budget for that. Sunsetting the project is mostly what it is right now is making sure that we're not leaving anything on the table in terms of insights that we can turn into artifacts that ACE can continue to use. So it's making sure that they're set up to sort of like milk all the value out of the data that we've been collecting, to have stuff in their hands that they can use for years ahead and not just for the next couple of months. We expect to be involved to some degree at a light touch way after this project ends. We don't have a financial model for that, but we think it's the right thing to do. So.
I'd like to take a quick moment for an online question that came in. There's a question that was asked. What do you find is the most difficult aspect of these kinds of community-based projects that is out of your hands?
Out of our hands, right. Francesca's going to talk a lot about that this afternoon. So I'd say tune into her session. One of the hardest things is just getting on the same page and building trust at the beginning. I think if you can do that right, then things get easier down the road. There's a million other things that are hard, like getting permissions to get sensors on light poles and managing City of Boston bureaucracy. Like that's a pain in the butt. But I think the thing that can most derail a project and lead to these power dynamics that are really unhelpful and lead to extractive work is just not getting on the same page and building trust. So it's hard, it's slow, and it's essential.
Why don't we close?
Yes, I got a quick question for you. Thank you very much. I'm interested in hearing Francesca's talk. I wanted to ask you a little bit about the beginning stages.
Yeah.
So I'm from New Jersey, and we're targeting a community that has incinerators and they have other stuff going on. And they're not very well organized, like, you were, they're pretty well organized, they want something, and you don't want to go and tell them you need this. But they do. So how do you kind of get them going in the right direction of, hey, air quality is important, it's affecting, they know it's affecting them, they're just, again, air is invisible, so what's your advice for that?
I don't have an awesome answer, and we've done projects with unorganized partners before.
Right.
It was way harder than with organized partners.
Yes.
And that's less like the logistics of organization and more it reflects partner buy-in and mutuality in the work. And so, I mean, my advice is wait.
Yeah.
Don't do anything yet. Like wait until there is real cohesion around some community priorities before actually doing any work. And resist the temptation to come with what you think the priorities should be. Yeah, thank you. Lots of open-ended curiosity questions help you do that.
Thank you again, Scott.
Okay, thanks for joining us for the first talk of our second session. We have Randy Lamb, who is an air quality scientist at the South Coast Air Quality Management District. Thanks, Randy. And he's going to be talking on the challenges and real-world lessons from multiple sensor network implementations in the South Coast Basin.
All right. Good morning, everyone. My name is Randy Lamb. I'm an air quality specialist at the South Coast AQMD. I'm representing the AQSEC team. And today I'll be talking about the challenges and real-world lessons from sensor network deployments in the South Coast Basin. So a little outline of what we will be talking about. I'll start off with a little bit about the background on South Coast AQMD, our jurisdiction. Then we'll move into our sensor networks, and then challenges and lessons, successes, and takeaways from our sensor network projects. So right here, we have a map of the South Coast AQMD. So I don't know if this laser point works. So right here in the middle is kind of where we're at in Riverside, California right now. And if you drive 2 hours west, you're going to be at our western portion near the beaches. And if you drive 2 hours east, we're going to be in our eastern Coachella Valley portion. So all of this is the South Coast AQMD jurisdiction. We have 35 air monitoring stations. This is 11,000 square miles. So it's a huge geographical area, 17 million residents. So, and very topography throughout. We have mountains, we have beaches, we have desert. So you can see where sensor networks can come and play here. I'm going to give a few examples from some of our different sensor networks. We have various sensor networks run by the AQSEC team here. And they're deployed on street lamps, on schools, at municipalities, just working with anyone we can to get these sensors deployed. Up top, you're going to see our private airfall network. So this is 70 plus sensors, located throughout the whole geographical region of our district. And down below, what you're seeing is a data dashboard that's built in-house. And we built this data dashboard because this data is private. The public can't really see it. So we ingest that data and then we display it to the public with the different community groups that we serve. So one thing that air sensors we found is really good for is filling in the gaps between where our different air monitoring stations are. And they're also really good for providing data checks for local events and enhanced events. One other big thing I'll talk about later on, I have a slide on, is the 5x5 kilometer gridded map. It's a blended AQI map that we kind of integrate sensor data into to display to the public. All right, so running a large sensor network. I'm going to talk specifically about this one sensor network that has over 70 sensors. Each of these devices has 4 plumes, PM2.5, PM10, NO2, and ozone. So this is a large network, like I said, it's spread out geographically, and it requires a lot of staff time. So we have 3 full-time staff dedicating about 30 to 50% of their working hours to manage this. That's 1 technician and 2 analysts. So the most time-consuming parts that we found is, first of all, logistics. So coordinating and planning where these sensor installations are going to be. You have to work with many different cities, many different school districts and individuals to make sure power is there, make sure data communication is there, and get them installed. Now, once they're installed, there's still a lot of maintenance to do. We actually had a lot of issues with power and data requiring us to send out staff, and just like something as simple as a simple reboot could take a couple hours with driving and troubleshooting. So something to look out for. And then when you're dealing with gas sensors, every 1.5 years, you have to replace the gas sensors. So doing that on 70 units is not to be underestimated. And then the last thing is quality control. So we perform health checks daily and calibrations monthly, and that's a lot of time. So the quality control really informs the maintenance and vice versa. So the next few slides are actually going to talk about how we do that. All right, so one of the tools that we use is a sensor health dashboard. And I would say that these are very important for managing a large sensor network, because your alternative, if you don't have this, is you're going sensor by sensor and checking the data, making sure everything's good. This saves a whole lot of time. This was an Shiny app developed by Eric Wall with input from the AQSpec team. And it's a really valuable tool for QC and making sure that we have data. So what you see on the columns, these are each individual sensors, right? Up top, you would normally see their sensor IDs, but they've been anonymized for this presentation. At the bottom, you can see the different subgroups that these sensors are put into based on geographic location. So you can easily see different trends that are going on with sensors. So like looking at this sensor group that's all grayed out, that's a communication issue. Maybe, whatever wireless providers having issues in that area. But this is really informative for what kind of troubleshooting you're going to need to do before you head out to the field. So it's not just going in blind. On the left-hand side, you can see different parameters that we monitor with this health dashboard. So up top is the PM2.5 sensor runtime. All these sensors have different runtime lifetimes. So keeping an eye on that is essential. Down here, you can see different things on the various gas sensors. So the ozone sensor, we have color coded. If it's pink, it's probably showing something that we need to address very soon. A lot of times that's flow with some kind of obstruction, showing that the data quality may not all be there, and to keep an eye on the sensor. All right, another lesson that we learned is that regular calibrations are necessary. So on the left-hand side, you're going to see a graph showing the PM2.5 gain changes over 2 years. On the y-axis, you're seeing the 2.5 gains, which are the slope adjustments that we're making for the calibrations. And then on the bottom, you're going to see the months throughout the 2-year period that we're running these calibrations. So you might notice with the PM, we're seeing up and down, like an ebb and flow. It's not just going up. And the reason for that is because really PM calibrations are, adjustments to the particle composition, right? So depending on the physical property of the particles that you're sampling, you need to adjust that calibration a bit. And then over here in the South Coast, we have an east-west phenomenon where during the fall season, we see the predominant wind patterns shift. And then we have to calibrate for that. So calibrating monthly and regularly, make sure that you're sensing for the right particle type. On the right, you see one more thing to mention is you see this guy that's kind of like having a line of his own. That indicates a sensor that's going bad. So this also, performing these calibrations monthly is also another form of QC check to see, okay, this sensor is probably not responding well. We have these limitations where if a sensor has a slope of over 5, then we're going to say that's probably not so good. On the right, there is a graph of the gas sensor gain changes over 2 years. So this is gas sensors, and what you're seeing is a gradual increase in the gain. And that's because for gas sensors, it's different. The changes to the calibrations are largely driven by sensor drift or age. So that's why you're seeing that increase. And then once it reaches a certain threshold, we say that sensor is probably not very robust anymore, and we switch it out with a new one. All right, so you've heard this all throughout this morning. The biggest challenge with community monitoring is communication. The success of community monitoring depends on communication and setting the proper expectations. In talking to various community groups lately, one of our recent projects, we found that most people are really interested right now in looking at air toxics and looking at fresh vehicular combustion, right? The first problem, we're working on that with air toxics. The AQSpec team is publishing VOC tests right now. Michelle Kwong and Wilton Moy have talks on that later this week, so go and check those out. In terms of vehicles, diesels, stuff like that, quite frankly, you have to communicate to the community, like air sensor technology is not there yet, right? We can't do ultrafines. The new research is showing purple airs, or plant towers in general are doing PM.1 to PM1, right? So, you have to, I guess, adjust expectations accordingly. All right, and then the last challenge that I want to talk about is varied responses in sensors. So what you're seeing here is a phenomenon that my ex-colleague, actually Claudia Oxendale noticed. She performed this analysis, but these are of some sensors out in the Eastern Coachella Valley region, where our primary pollutant of concern is going to be dust, PM10, right? So this is a wind-blown dust event where we have high winds and lots of dust. So on the left, you're going to see the PM2.4, sorry. On the left, you're going to see the PM2.5 graphs. In the black line, you're going to be seeing the reference instruments. In the blue line, it's kind of hard to see, is going to be one sensor model, and in the red line is a different sensor model for PM2.5. And you see that the blue sensor is actually tracking quite well with the reference instrument. And this is a high dust environment, high wind environment, right? The red one is actually kind of tracking, but at, like an order of magnitude lower. So it is, still picking some stuff up, but you have to really be careful with PM2.5 in high wind environment with certain sensor models. On the right is a more interesting story. This is the PM10. So you can see the reference instrument is going up to, what's that, 1500. The blue sensor model is tracking pretty well, surprisingly, for low-cost sensors. And then sensor B is almost not picking it up at all, right? So these are both low-cost sensors. This isn't, a bigger study in any way, but we have noticed this multiple times during high wind events where one sensor model can pick up the PM10 and the other sensor model cannot. So it's kind of hard to say a blanket statement as, low-cost sensors can't pick up PM10. Some can, right? So look to AQ spec evaluations, look to other literature. One thing that I think people should take away from this is if you're doing a community monitor project with multiple sensor types, it's very important to know this information, because if you're displaying PM10 for both of these values to the community, that's going to cause a whole lot of confusion. So, in our case, we don't show PM10 for sensor model B, the red line, because, it's not picking up what the reference instrument is picking up. So this can inform your decision. All right, so just to wrap things up a little bit, some successes from our previous sensor monitoring projects. On the left-hand side, you're going to see these are both actually community-generated reports. On the left-hand side, we had a really gung-ho community member create a video using the data from their purple air sensors, which is really cool. Shows a lot of community engagement. On the right, we have a collaboration between a local university and API-FM, which is a community group, where they created a report about the sensors at a high school, and they even gave recommendations to not have PE classes during times of rush hour traffic. So, some successes in the community there. And then just really quick, our sensor dashboard in-house I talked about earlier. This is really good for sensors that have kind of a paywall. You can push through sensor data with various helpful tools like a calendar plot or historic graphs, just so community members have easier access to the data. And then the last thing I want to highlight, Scott Epstein talked about this earlier, but we integrate sensor data into a blended AQI map for our, the people in our district. So if you go to the South Coast AQMD website, we have this 5x5 kilometer gridded map, which takes into account sensor data, PM2.5 sensor data, using a tree principle, along with reference instrumentation and chemical transport modeling. So that's a really big success in how we use sensors in, as government agencies. All right, so a few key takeaways. I'm just going to focus on the middle two dots, but I know I'm over time. Sensor networks are not set it and forget it, right? They require a whole lot of work. That's the theme of this morning, I think. And to retain high data quality, you need eyes on the project and you need boots on the ground to make sure everything's fixed in a timely manner. And then regular calibrations are necessary, auto QC checks are necessary, and sensor health checkups, dashboards are necessary when displaying data to the public. All right, so thank you for listening. I want to thank the AQ Spec team and everyone at South Coast AQMD, along with some of our collaborators. We also have sensor guidebooks for community monitoring. If you want to take a look at that on our website, we have physical copies at our booth. I know there might be a lot of questions, so feel free to visit us and we'll be happy to answer any questions. Thank you.
Thanks, Randy. A few questions came in on the app, and one of them I definitely wanted to ask as well, which is the availability of that awesome R-Shiny app. Is that something that might be available for others to use?
That's a good question. We didn't develop that app. So about that. Sorry.
Talk to who?
Eric.
Okay.
Yeah.
Yes, thank you very much, Detlef Helmig. You noted in your talk that remote calibration capabilities for ozone and PM2.5 was really important or valuable. How do you possibly do that? Just not aware how you can do that.
Yeah, so there, what we're using is something called a moment matching calibration or MoMA calibration. There is a paper published on there. It's on the link there. You can go to the AQSec website, and under our papers, you can find that as well. But basically what it does is it does require a proxy reference station. So this is using, you know, for PM2.5 and for ozone, we're using distance, the nearest reference station. And we're kind of trying to match those peaks and troughs of the sensor data just to make sure that we're, you know, kind of in the ballpark. Yeah.
Hi, Randy. Thank you. My question is on your PM2.5 retrieval in the dust storm. So it shows that there's actually a ton of mass happening between 1 and 2.5 microns. And you noted that you don't report PM10 from these sensors because you know they don't work for that. But I would argue reporting PM2.5 in that situation is also highly problematic. How do you reconcile that?
Yeah, that's a good question. You know, I think that's a question that we need to visit a lot. And right now, with the sensor technology that we have, you know, we need to put something out there. And if the alternative is to not do anything, I don't know if not doing anything is the answer either. But yeah, that's a serious question that I think the community needs to address. Yeah, I don't know if I answered that. Sorry.
Thank you, Randy. All right, our next speaker is going to be Ian Longley, who is a principal scientist at the National Institute of Water and Atmospheric Research in New Zealand.
Great, thank you. So this is going to be like my greatest hits. So my era's tour, if you like, but unlike Taylor Swift, hopefully it won't last 3 hours. New Zealand is surrounded by the Southern Ocean, which gives us pristine background air. But if we hide a little secret is we pollute that air quite heavily, especially through the uses of solid fuels for home heating, particularly wood. So what I'm going to talk about is a series of projects going over the last 9 years, which we collectively call Community Air. There's a research strand, which we started in 2015, CONA, which is really looking at new technologies. And we have some spin-off projects which are provided as services to the community, but follow the process of behavior change. So there's growing awareness, there's participation in monitoring, and there's taking action and evaluating that action. So I'm just going to give you a scatter shot of best bits of these projects. And of course, this is the Air Sensors Conference, so it's all driven by air sensors. And what we've done is deployed, or rather adopted, one or more small New Zealand towns each year. Sometimes we've gone back, sometimes we've done multiple towns in one go. And we've been on the rise with the development of air sensors, a range of devices, some of which we've devised ourselves or put packages together ourselves. More recently, looking at commercially available objects like the Clarity and the Qingping. And what we're really doing is we're exploring the potential of new sensor and data technologies to obviously measure more places, observe and characterize more atmospheric processes, but also to enable wider engagement, participation, and empowerment. And largely what we do is we use ambient networks as a platform for a whole range of other activities. So this is where we started. I hope you can admire the build quality there. This is our first device, Pac-Man 2015. Basically a different sensor on each of the faces, 6 faces of the cube, making it easy to assemble. So this was particles, CO, CO2, proximity, movement. And all the pain. It was based on a sharp PM sensor, which had a lot of interference, a lot of codependencies. It was a lot of pain trying to extract the true signal from the noise and the interference. Then the plan tower came along and we went, hallelujah, we don't have to do all that again. So we built the Odin, which is a remote device built from a toolbox you could buy in the local hardware store. With a PMS inside. We built quite a large number of these. One of the tricks we found is we'd like to deploy them on streetlights or power poles. And if you have a long piece of wood, you can strap your instrument to one end, assemble a piece of wood, strap that to the pole. There's no ladders required. There's no anything. And that was really good for getting easy permissions. So what we do is we take data from this Odin network, and I happen to work next door to the weather forecasters in my institute, so we can piggyback on their animation capabilities to produce images like this, which we've used really as a communication tool, because what they really show is how incredibly dynamic air quality can be, especially in our towns, where we're going from almost pristine outside the town to heavily polluted inside the town. So a lot going on. We've been able to create maps like this, which shows the long-term average pattern of pollution in various towns. We allowed this data to be downloaded by participating schools so they could do their own investigations. And doing some exploring, sorry, the title's come out wrong there, but that says children as data analysts. So we've done a fair bit of work on enabling 11, 12, and 13-year-olds to come up with reports based on real data that we collected. We created a website where we basically, building on the idea of YouTube almost, is posted short questions for the children to answer. I encourage them to record short videos of their answers and then pose questions for us, which we could then share amongst our research colleagues and gave a little bit of a dialogue. Quite difficult to maintain over time, but a really promising tool, I think. So after putting the Odins out, we had indoor sensors as well. We tried a number of different sensors and a number of different ways of distributing and managing them. This is my friend Colin, a former teacher who took on the job in one of our towns. We've used the local museum as a distribution point, and we've used schools as a distribution point as well. This particular device, the HoHo, which we've stopped using now, but it just, I just wanted to show where we had a QR code on the top and allowed householders to scan that. That gave us a record of where that instrument is, but then allowed them access to the data. So it was a nice little exchange. We've been experimenting with how we feed back results to householders. This is an example from a home where the thickness of the line is just the level of PM in the home. There's so much information here, which the householder were generally very able to understand. You know, you can look at the events that are happening, emission events. You can look at infiltration. You can look at decay time in the home. These were emission events where there was a sudden jump in particle levels. The orange is where we saw a jump in particles and CO2. The blue where it was particles only, giving us a clue as to whether it's a dust event or a combustion event. And as you can see, over time, the pattern in time is changing. So we would talk to the householder and then we go, oh yeah, you know, I'm not lighting my fire so much now. And this is the time I'm in the kitchen. We love to combine indoor and outdoor data. That is so much more informative for householders, because now they can see the relationship between, you know, what I'm doing in my home, what's happening outside. Is the outdoor polluted air getting into my home? The answer is almost, in every case, almost certainly yes. And they don't understand micrograms, but they do understand mine's the most polluted home in town. So what we do is we give them charts like this saying which quintile within their town or within their study they sit, and that gives them a sort of relativity, which is often much more useful than just giving them a raw concentration. We use the data to drive some indoor-outdoor apportionment modeling. So effectively, we fit an empirical model of infiltration, smoke, PM coming from outside, and the residual, what's left, is what was generated indoors. I could spend a couple of talks on that, I'm not going to. But it allows us again to give feedback information like this. So this is one home. You can see what's happening outdoors on average. How much of that is getting indoors? About 50%. But there's also this indoor generated component as well, which is stronger in the kitchen, clearly implying cooking sources. From a research point of view, we do that over a large number of homes. We start to get a lot of more information about the housing stock and the way people are using it. Each dot on this chart is a home, and it's on a matrix of how significant indoor sources were and outdoor sources were. So we can start to think, you know, which intervention would suit these different homes. Another thing we tried is putting temperature sensors on their heater. From a regulatory point of view, one of the biggest unknowns is what the variability in time in emissions. It's an important input to dispersion modeling and something we usually don't have. But by combining this data from multiple homes, not only was it interesting for the householder, but we were able to put together data on how many homes in our town are burning wood at any given time of the day, how that is influenced by the weather. And generally what we found was that people heat their homes based on the previous night's weather. In other words, what they anticipate tonight is going to be like has a little bit of habit built into it. A fair bit of work we've done on communicating. One of the most interesting projects was communicating air quality to the under fives. Clearly, we've not been able to use PM2.5 concentrations here. So what we did is we put a bunch of sensors in a box, linked it to a screen, and we animated the screen based on what the sensor was doing. So a child could blow on the dust sensor or the humidity sensor, and the screen would animate in response to what they were doing. Lots of potential there. Augmented reality is absolutely great. We worked with some artists. We did a gallery where there was a tree stump, but if you look at it through a mobile phone, you see the tree, and the tree was animated based on weather data, which made the leaves flutter, and was animated by air quality data, which made the animals come and land on the tree because they liked it. A lot of material we generated over the years, we've put on a website which we call Schools Air Watch, and it has a bunch of activities, including making your own measurements. This is actually a device created by a student, which we gave to some children, and they went around the school and they mapped air quality and they put stickers on the map, and over time you can start to see patterns emerge. Again, simple ways of communicating and sharing air quality learning. We're currently working with an organization called the House of Science. We have a poster about this. House of Science is a charitable trust which provides teaching resources to elementary schools, which basically rent them for a week. So we've created an air quality box with air quality experiments and a monitor in each box. We also are collecting all the data. So this becomes basically a roving monitoring station. So these are available for rental by schools across New Zealand starting this month. We've moved recently to the Clarity devices, which are very easy to install, where we're exploring how we can train people easily to put these things up. And one of our latest ventures is Smart Home Air Quality System, which we also have a poster on, where really we're piggybacking on the smart home automation industry that's rapidly growing. So these are devices that will talk to each other, and are open source software tools to make them talk to each other. So not only are we recording air quality data, but we're recording proxy data that influences air quality, you know, basically how well the space is ventilated and how much the space is used. We can feed back that data either in a real-time dashboard, what's the air quality like now, what should you do now, but also as we give weekly summaries, so you can start to look at patterns and think about changes in usage. And I think my final slide is we're starting to explore with enabling people to assess air filtration devices, portable air cleaners, using our indoor-outdoor source apportionment technique. So you can see here is a home which was using an air filter, and we're able to report on how much impact it had on the indoor-sourced PM and the outdoor-sourced PM separately. Thank you very much. I didn't go on for 3 hours, I could do, but there's plenty there, so please have a look at my posters and feel free to contact. But thank you very much.
We've got an online question, and then everyone else can chime in as well. Question about ventilation. Did you do any aspect of ventilation measurements, or look at things like kitchen exhaust monitoring, or decide which homes had air purifiers, et cetera, as you were looking at that indoor air quality data?
Great. So I guess our original motivation was to look at infiltration, assuming that the hazard is outside and we're protecting people from an outside hazard. This radically changed with COVID-19 because the hazard was now inside. So what we've been really doing is working with a wide range of localities, particularly buildings that do not have mechanical ventilation. And during COVID-19, we were particularly concerned with places that vulnerable people can be found. In New Zealand, only about 10% of our schools have mechanical ventilation, 90% rely on opening the windows. So this work has very much been oriented around using the natural dynamics of indoor air quality, the rise and fall of CO2, the indoor-outdoor exchange of particles as tracers to infer what's happening with the ventilation, and particularly that indoor-outdoor exchange. So although I haven't presented data on it, one of the things that we extract from the data of all the places we visit are the range of real-world air change rates that are achieved in that location. And where we're moving, one of the directions that we're moving forward is to enable the facilities managers and the households to understand what the building is capable of, as opposed to what's actually being achieved now and how we can get closer to that capability.
Thank you.
So our next invited speaker is Boris Lukhanov, and he's a senior scientist at PSE Richmond. That's the physicians, scientists, and engineers for healthy energy. And he's going to be talking about the Richmond Air Monitoring Network. Next slide.
Thanks, Dave. The Richmond Air Monitoring Network included about 50 locations in the cities of Richmond, San Pablo, and North Richmond. That's in the East Bay of San Francisco. We deployed the monitors for a period of about 2 years. And this is a pretty small area of about 10 square miles. And so this resulted in a pretty dense, large, dense network of air monitors, about 5 monitors per square mile. And so we were able to basically deploy them in each of the neighborhoods, several monitors per neighborhood in the entire area. The area is home to some of the most environment disadvantaged communities in California. There's over 100,000 people living in the area. Most of them are minorities and environmental justice communities. Richmond has some of the highest asthma rates in the state, and also multiple sources of air pollution, including 3 major highways with heavy traffic. There's a major refinery, the Richmond refinery. There's a coal terminal in the port, lots of industrial facilities. And despite all of that, there's one single a regulatory air monitor that's tracking criteria air pollutants in the area. So the goal of the project was to get more insight into the patterns, sources, and of course, the actual levels of air pollution that the communities are experiencing in the area. The Richmond Air Monitoring Network is also perhaps one of the first, maybe the first large network to deploy black carbon, low-cost black carbon sensors along PM, NO2, and ozone sensors within such a large network and such a long period of time. The black carbon sensors were deployed over 2 shorter periods, 1 month in the winter and 1 month in the summer of 2021. And all were co-located with the other sprinklers. These are the instruments we chose for the project. We use the AeroQual AQY air monitor. It uses a light scattering PM sensor that's similar in performance to the popular Purple Airs. It has an electrochemical NO2 sensor and a metal oxide semiconductor ozone sensor that's patented by AeroQual. Also has internal temperature and RH corrections. The aerosol black carbon detector is a custom-built detector by Lawrence Berkeley National Lab and UC Berkeley. It's a filter-based absorption photometer that's not commercially available, but was available for this project thanks to the collaborators at Tom Kirkster's lab at UC Berkeley. I'm going to talk a little bit about the challenges that were encountered in the project. As many of you know here, all low-cost air sensors tend to drift over time. This is also true for reference monitors. The bias and drift are caused by different sources, depending on the time scales you look at. So on short time scales like minutes and hours, there are cross interferences across pollutants like ozone and NO2. Temperature and RH can influence the sensors as well. So the solutions normally are embedded in the instruments as software or hardware corrections. On longer timescales, we saw dust accumulation, sensor degradation. Also, there's seasonal changes in PM composition. So those causes for bias and drift are generally solved by more frequent calibration and maintenance. And finally, over longer time periods, like our project, there's mechanical wear and tear of pumps and fans, there's corrosion, electrolyte changes, and so on. And so those are actually harder to fix with calibration, and so sensor replacement was needed for a lot of the sensors. We also had an initial co-location period at the CARB facility in Sacramento. The point of that was to evaluate sensor performance and inter-device variability, and also get initial co-location initial calibration parameters for the sensors, like gain and offset. During that multi-month co-location, we saw a significant drift, especially for the ozone and NO2 sensors. And so at that point, especially after transferring the sensors back to Richmond, the NO2 sensors showed even more drift. And so at that point, we knew that we would have to likely calibrate the sensors more continuously because the initial calibration parameters were not working anymore. Of course, the large number of sensors in the network made individual site calibration very problematic logistically and also prohibitively expensive. So our approach was to do remote network calibration. And there was already a question earlier about this, so hopefully this can clarify that question. So the network calibration we chose was the moment matching MoMA calibration developed and patented by Airqual. The MoMA calibration essentially can calculate offset and gain for each sensor by matching the data probability distribution of the data of the sensor to that of a proxy reference site. So it matches the mean and variance in the data to that of the reference proxy site. And so this is useful for detecting drift and correcting a drift, especially in gas sensors like ozone and NO2, and also useful for correcting seasonal bias in the PM sensors. This worked really well for us. We were receiving monthly calibration parameters from Airqual, improved the ozone and NO2 data substantially. With the PM data, I think the jury is still out, and I'll talk a little bit more about that in the next few slides. There were so many challenges with the PM data. We co-located 2 AQIs at the Air District Regulatory Site in Richmond. Those monitors are plotted here on the scatter plots against the reference monitor. And this is hourly data from the second half of 2020 during wildfire season, so the PM values are very high. You can see at the bottom that the MoMA calibration corrects for overall bias, and adjusts the slope and the zero offset the data. However, we also saw a really strong PM dependence on relative humidity. The data is colored by relative humidity. And we looked at that in more detail. This is a 1-week period during wildfire season. The 2 co-located sensors are colored in red and blue here, and the reference monitor is in black at the top. And you can see how RH is plotted at the bottom, and you can see how at different values of RH, which change diurnally, you see how the RH correction sort of at low RH kind of overcorrects the data and really bumps it up, and at high RH it does the opposite. So the overall mean values are sort of correct, but the actual data points are sort of bifurcated. This is what we saw in the scatter plots. We contacted Airqual about this, and because it's a proprietary RH correction, the options we had were either to use it or not to use it, and using it was better for the lower PM ranges, but it didn't work obviously for the higher PM ranges. And then the opposite happened with the non-corrected data. That worked much better with at the high PM ranges, but the normal range that we operate at is the lower ranges. So we basically what we decided to do was to try to reverse engineer what Aircall algorithm was. So we reversed the growth factor scaling for different RH bins to effectively negate the correction during high PM events only, so during wildfire events. You can see on the right that that at the bottom, after that, it really took care of that problem, and individual sensor bias was still calibrated with the MoMA calibration, by the way. So we kept that as well. And then at the lower PM events, we kept the RH correction going. I wanted to show you some temporal trends of black carbon, PM, and NO2 from our data. This is a busy graph, so I'll try to explain it slowly. On the left-hand side, we have weekday average network concentrations by hour of day. And on the right-hand panel, we have the weekend values, again, by hour of day. We have winter values, which are colored in purple, and then the late spring values, which are colored in green. And the solid line is the average network values. The shaded areas show the 95% confidence interval. So that's the variability across the network. And we saw that average black carbon concentrations were much higher in the winter, about 3 times higher than in late spring. This is mostly due to local meteorology. There's a lot less wind in the Bay Area in the winter, and also there's a much lower boundary layer, which sort of traps air pollutants and prevents them from dispersing, especially primary air pollutants like black carbon. We also see much higher variability of black carbon compared to PM2.5, especially in the winter. There's a clear morning and evening peak, so that can be associated with traffic patterns. The black carbon morning peak also coincided with NO2 peak, which suggested high diesel emissions, likely from heavy duty trucks in the area. In contrast, we see sort of pretty modest diurnal patterns for PM2.5. So that suggests that the PM levels that we see are likely driven by regional emission sources and probably secondary PM formation. We also saw that on weekends, evening peaks in black carbon and NO2 were pretty high, and they kind of persisted throughout the night. So that suggested perhaps other potential sources like residential wood burning. This is a graph that shows the spatial variability of PM and black carbon data across the network. These are average concentrations by air monitor, and they are sort of rank ordered by how much they vary across the network. These are normalized concentrations. So you can see that there's much greater spatial variability across the black carbon sensors compared to PM2.5. So this suggests that black carbon is probably more indicative of local emissions, while PM is again more indicative of area sources or regional sources and secondary PM formation. It's also possible that the MoMA calibration may be partially responsible for the lower variability in the PM data, because it tries to match that data to the proxy reference site. We tried using also the non-calibrated data, and that did have more variability. However, it was still not as much as black carbon, and also it was poorly correlated with the black carbon, still unlike the NO2 data, which was very highly correlated. So that suggested that black carbon is really more indicative of local sources of air pollution. This is my last sort of technical slide showing spatial trends of black carbon specifically, concentrations across individual sites in the network. These are normalized again to the network average. So the red means higher than the network average, and the blue means lower. And so you can see, oh, and by the way, some of the sites are numbered. These are the sites that had the highest or the lowest concentration consistently throughout winter and late spring. So they were persistent sites with high or low concentrations. And what we see is that the sites that experienced the higher black carbon tended to be very close to highways within 500 meters of major roadways. And they also tended to be closer to industrial areas and the major rail line. Location with the lowest black carbon were all in residential areas, sort of to the west and up in the hills that you can see on the right-hand side. A few highlights and takeaways. We found that the combination of PM and NO2 and black carbon is quite powerful in identifying local pollution sources. We see much greater spatial temporal variability and also, locational persistence of black carbon compared to PM. So these suggest that black carbon is likely much more informative than PM of, local proximity to emission sources and of their activity. And one of our highlights and recommendations here is that black carbon and PM could be used for greater insights into community air protection plans. Lessons learned, those were shared before by several speakers, so I'm not going to repeat them. But I will focus on the last two a little bit. We found that ongoing drift detection and remote calibration, which we did through MoMA, are quite critical, especially for the gas sensors, ozone and NO2. For PM sensors, the value of using MoMA is less clear to me. There might be trade-offs between, correcting for seasonal bias, like seasonal changes in PM composition, versus maybe inadvertently affecting the variability in the data across the sensor network. So that's something to keep in mind and be aware of. Thank you for listening. I want to acknowledge our collaborators at UC Berkeley, Tom Kirkstetter's team, and the lead author of the paper, Rebecca Sugru, and also our team. Also, I want to mention our community partners on the ground, APEN, the Asian Pacific Environmental Network, who were really helpful with finding hosts. Thank you.
Yeah, so I have a quick one. Now looking back, you did a very dense network there. Would you choose to keep it that dense? Would you do it less dense? What do you think kind of was necessary in the area that you were looking at?
I think I would think about it depending on the sensor. So for ozone, the variability was not as high across the area. There was still some variability, but for the PM and NO2 data, it seemed that kind of high density is important to really get a good idea of where the local sources of air pollution are, especially as you can see in the black carbon data, some of those air monitors were lighting up because they were within a few hundred meters from roadways, and then the ones that are just below the remove were not. So it seems important to keep that density high or even higher. Of course, that comes with trade-offs and costs.
Great, thanks, Boris.
Thanks.
Our final speaker of our session here before lunch is going to be Ethan McMahon, President of EM Environmental Solutions. Take it away, Ethan.
Good morning, everyone. My name is Ethan McMahon. I'm with EM Environmental Solutions. My co-author, Ajay Nagpur of Princeton University, could not attend the conference today. But before we get started, I'm going to take a look up here at me for a second, and I'm going to do a quick poll. I'm going to ask you a question, and then I want you to raise your hand for which of three options that fits best in one air quality project you're involved with. So the question is, what's the main focus of your air quality project? And there are three choices, I'll tell you them. One is monitoring, education, or action. So get ready to raise your hand for one of those things, monitoring or education or action. There are about 50 of us here, and I'll gain some information if we do this. So main focus of folks for monitoring, raise your hand. It looks like about 25 out of 50, half the people. Second one is education, main focus. You can only vote once. So that looks like about 3 out of 50 and 6%. And for action. 1, 2, 3. That's 15 to 20. So let's maybe 20 out of 50. That's the best news I've heard all day. Thanks. And what I want you to do today in this talk is I want to actually have more bias in air quality. But I want to have it not be a bias about data. I want to have it be a bias towards action. So that's what we're going to talk about now. So you all know the health impacts from air pollution on cities, and they can be very high. Chronic obstructive pulmonary disease, heart disease, and asthma are 3 of the big ones. And just here's how that looks for 2 cities. For Nairobi, Kenya, that's about 300,000 asthma cases in 2019. And for another city in India, that's about 400,000 asthma cases in 2015 to 2016. So it's really a big problem at the city scale. And we know that there are many benefits to acting to reduce air pollution. You have better health, maybe in terms of fewer children having asthma incidents. We have less impact on climate change with reduced greenhouse gas emissions. And we have a better quality of life, for instance, with less traffic. And also people would have more peace of mind, which is nice too. And I'd say though that the world has made a lot of progress on air quality. So for measurement, there's a huge amount of coverage now. Almost 7,000 cities have sensors, and that's a lot. The calibration equations for different situations have been worked out. And on the data management front, people have figured out how to manage error corrections and data storage and come up with data formats to help organize the data and make it integratable. And regarding funding, there's some funding from EPA community grants, the Clean Air Fund, Bloomberg, and others. So a lot of the funds are going in the right direction. It's great to have all the support, especially from the Clean Air Fund and their recent announcement about black carbon in the last few days. But many city air quality projects still are focusing on measurement, unlike the folks in this room. So I took a look at the 132 grantees for EPA's American Rescue Plan Enhanced Air Quality Monitor grants. And about all of them do measure air pollution. That's on the far left. And the measure on the left edge is % of projects that work on these activities. About half the projects plan to work on outreach. For these 132 projects, about all of them worked on measurement. Half of them worked on outreach. Maybe 15% worked on evaluating potential actions, and only 5% said they were going to take action with that grant. That's the stated goals. So the goals are mostly about measurement. All right. And maybe that's what they were designed to fund in the recent a huge amount of money that really helps a lot of communities. But it's concerning to me, at least, that so few of them focus on taking action. Some cities are actually taking action without having complete information. So they have some data already, such as pollution concentrations at different times of day, approximate contributions of sources, for instance, regarding transportation. In developing countries, transportation can contribute, and developed countries, transportation can contribute to about 15% of emissions in a city. But in low and middle income countries, transportation can contribute to maybe 50% of emissions. So we have some basics there for the contribution of some sources. People also have information on health impacts, maybe from health agencies and hospitals, and there's a political appetite for some actions. And let's see if any of this is working. Right. So how can cities achieve health benefits sooner? Well, cities can change the focus of air quality projects to be about action, the focus. Funders can provide incentives to encourage and reward action, and agencies and practitioners can provide paths for taking action. And here are some ingredients for taking action. You've heard of these already before: willingness to act, ability to act, and also information about the city. And of course, every city is going to use its own ingredients to get to action based on their situation. So next, I'm going to get into each of these three areas. So for willingness to act, if you have an enthusiastic mayor and you're working in that city and they want to work on air quality, you have hit the jackpot. Okay, this is a rare bird. or a unicorn, but these mayors are willing to take action quickly and decisively. And for instance, you know about London establishing an ultra low emission zone for Breathe London, really driven by the mayor's energy. Other ingredients about willingness are things like having a clean reputation for your city to uphold. Politicians that are willing to act with incomplete information. You may have supportive agencies or a high portion of the public supports action. And on the ability to act, and these ingredients include having regulatory authority to set pollution standards and enforce them, having resources, especially funds or data, having buy-in from stakeholders, including city residents, and having expertise, which often can be obtained to some degree by using resources. And finally, information about the city. It helps if cities know something about estimates of health impacts and trends, have some understanding of the sources of pollution, understand the process for getting to action. They know what actions are possible and their associated costs, benefits, and timing, and if they know how to set a target that's achievable. So here are some examples of how 3 cities have taken action. So for Nairobi, Kenya, with a population of about 4.4 million in 2019, they are expecting rapid urbanization in the next decade. So they're preparing ahead of time. Their approach was that they passed an air quality law and they're drafting an air quality plan. So there's definitely willingness to act there. And they're also developing a set of potential actions that reflects those goals in that plan. And the results are in process, but they're evaluating actions based on their political feasibility, effectiveness, and so on. A second example is Surat, India. It's a little bit bigger city, 6.1 million in 2016. They had municipal solid waste and construction dust as environmental problems. And they actually had managed to become the second cleanest city in India, but they became out of attainment for air quality, so they were concerned. And in their approach, a group provided data on waste burning in collaboration with the city and implemented waste management techniques and implemented dust reduction techniques for construction. And the results were impressive. They reduced waste burning from 3% of the total generated waste to 0.5%. And they also reduced on-site waste generation from construction activities by 90%. And these are cost-effective and practical solutions that were done in close collaboration with the government and industry. The third example is Curtis Bay in South Baltimore. The context is that it's a lower socioeconomic status neighborhood. They had dust in their yards and houses and a nearby coal transfer station, and they have illnesses that seem to be at high rates for asthma and lung cancer. And so their approach involved working with a local university, Johns Hopkins University, and others to help the city apply for and receive a grant from EPA. So the universities measured air quality levels and emissions from trucks that transport coal. The universities also confirmed that coal dust was the source of this observable dust after a 1-year study. And the results were that they're considering a few options, such as covers for coal in trucks, evaluating synchronizing traffic lights so those trucks that have the coal can idle less. And residents are proposing changes to the facility's operating permit. So just the bottom line here is that cities can and should act sooner. They can make action the focus of their air quality efforts. They realize that it's possible to act without having complete information and without having the perfect be the enemy of the good. And they realize that their citizens will benefit sooner and their residents will suffer less. So I'd like to hear your ideas about how cities can act sooner to get benefits sooner. Thank you.
Hi, thank you so much for your presentation. I work on Breed London. Thanks for the shout out. You spoke a lot about bias towards action, emphasis on action. Can you talk a little bit about the scales or kind of, because action is a big word and I just can't help but think action according to whom, you know, how are you defining that, understanding that through your work?
Yes, I'm thinking of actions in terms of not protective steps where people can protect themselves, like the fellow from New Zealand who talked about You could give warnings and tell people when the air was polluted so they could reduce their exposure. I'm calling that kind of prophylactic, but it's not addressing the causes. So I'm talking about actions that address causes. And actions can have a broad range of activities. It can be synchronizing traffic lights. It could be a new policy or law that takes years to implement. So that's the kind of thing I'm thinking of. Actions that deal with outcomes that include better health of people and address the problem so that more people are still not affected. I hope that clears it up some.
All right, thank you. And thank you to all of our speakers at this session.